Alright, so for this video, let's go through and review our rules for taking derivatives of our inverse trig functions. Remember that the first thing you should do with any inverse trig function is just remember the form that you're more comfortable with. If you have y equals the inverse sine or arc sine of x, we can rewrite that as the sine of y is equal to x. And that is, of course, our ratio of opposite over hypotenuse. And so I can use this to start laying out my triangle. I know that the side that's opposite of my angle is my x. My hypotenuse is equal to 1. You can use Pythagorean's theorem to find this side, and that will be 1 squared minus x squared. And then what we're going to do is we're going to take the derivative of the form we're more comfortable with respect to x. When we do that, the derivative of the outside, we'll have to use the implicit differentiation here. The derivative of my outside here is going to be a positive cosine of y times whatever dy dx is. And the derivative of x, of course, will just be 1. Now keep in mind, right here, our whole goal is to find what does dy dx equal. So we've got an equation that's set up for it now. We know that dy dx is equal to 1 over the cosine of y. And from our triangle, we can see, well, let's go ahead and put that as a secant of y first. The secant of y, secant is hypotenuse over adjacent. So here's my hypotenuse. Here's my adjacent. 1 minus x squared. So my derivative of the arc sine is 1 over the square root of the square root of 1 minus x squared. We'll use the same trick throughout the problems. So here, I can rewrite this as the cosine of y is x. This is adjacent over hypotenuse. I can list the adjacent side, I can list the hypotenuse. Here I can list what this other side will be using Pythagorean's theorem. I'm going to want to take the derivative with respect to x of that form that I learned the rule to. I'm going to need to use some implicit differentiation. And I get negative sine of y times dy dx is equal to 1. Therefore, my derivative of y is negative 1 over the sine of y. In other words, a negative cosecant of y. And that is equal to negative, that's cosecant is hypotenuse over opposite, 1 over the square root of 1 minus x squared. And there's our derivative. Let's see. I know I probably shouldn't go back and try to circle those. I'll just make a mess of it. But there's our derivative. Again, with a tangent. This tells us that tangent of y is equal to x. This is an opposite over hypotenuse. Oh, sorry, that's sine. Opposite over adjacent. I'm going to take the derivative of my function and I get out, let's see, derivative of tangent is a secant squared times your dy dx is going to equal 1. So our derivative is going to be the same thing as 1 over secant squared of y, which is the same thing as cosine squared of y. Well, let's see, I hadn't put my triangle together yet, not too late. Opposite side will be x. The adjacent side will be 1. My hypotenuse here is going to be x squared plus 1. So my cosine of y will be the adjacent side over the hypotenuse. And then because I have a cosine squared, I'm going to want to square all of this. And finally I get that the derivative of the arctangent is going to be x squared plus 1. Repeat for cosecant. Here we have that the cosecant of y is going to be equal to x. This is the hypotenuse over the opposite. So in this case, here's where my x goes. Here's where my 1 goes. We can use Pythagorean's theorem to find the last side. We're going to take the derivative of our equation with respect to x using implicit differentiation. So the derivative of a cosecant, you guys, I know I have to look this one up sometimes. This one's equal to the negative cosecant times the cotangent. Now, this is the derivative of this. Don't try to take the derivative of this again. Don't use a chain rule. Just write down what that derivative is equal to, and then we have times the dy dx, and all of that will equal 1. So our derivative is going to be the same thing as negative 1 all over the cosecant of y times the cotangent of y. I'm going to erase a little bit of this so I have some more room. And that's the same thing as the negative sine of y times tangent of y. My sine of y, it looks like, is going to be 1 over the square root of x squared minus 1. My tangent is going to be 1 over, oh, I got those backwards, didn't I? That's my tangent. We'll go backwards. If I knew how to edit, I would, but obviously I don't, so that's all right. Okay. Back again. Opposite over hypotenuse, opposite over adjacent. I'm going to bleed into the next section just a little bit. That gives us that the derivative of an arc cosecant is negative 1 over x times our square root of x squared minus 1. For our secant, we'll get something similar. Here, that your secant of y is equal to x. This is the same thing as hypotenuse over adjacent. So here goes my hypotenuse, here goes my adjacent. Use Pythagorean's theorem to find this third side. Take the derivative of the secant of y equals x. You will get derivative of secant is tangent times secant. Again, you're not going to chain rule this. This is just what the derivative is, so you just replace it when you take the derivative. And then you are doing implicit differentiation, so times the dy dx. And this is going to equal 1. So dy dx is going to equal 1 over tangent of y times the secant of y, which is the same thing as cotangent of y times cosine of y, which gives us, let's see, adjacent, oops, wrong one, adjacent over the opposite times adjacent over hypotenuse, and that will give you the same thing as our arc cosecant derivative, except for with the positive. Last one of all, our cotangent, or our arc cotangent, our inverse cotangent, we can rewrite in terms of the angle. This is the adjacent over the opposite. So here's our adjacent side, here's our opposite, here is our hypotenuse. Up in the corner, there's my notification about publishing your videos. Should be published soon. All right, we're going to take the derivative of our cotangent of y equals x equation, and we will get out, let's see, derivative of cotangent is a negative cosecant squared times dy dx, and then the derivative of the other side will equal 1. So dy dx will be the same thing as negative 1 over cosecant squared of y, which is the same thing as a negative sine squared of y, which gives us, let's see, opposite over hypotenuse squared. So here are your derivatives for each of the trig functions. I'll rewrite these for you. Just our conclusions here, and hopefully you have them in your notes. When you take the derivative of an arc sine of x, you will get out 1 over the square root of 1 minus x squared. When you take the derivative of an arc cosine of x, you'll get out the same thing, but it will be negative. When you take the derivative of a inverse tangent of x, you will get out 1 over 1 plus x squared, or of course 1 over x squared plus 1. Derivative of an inverse cotangent will give you the same thing, but opposite in sign. The derivative of a arc cosecant of x is going to give you negative 1 over x times the square root of x squared minus 1. The derivative of the arc secant, or inverse secant, will give you the same thing, but will be positive. And what this does for us is it gives us more integrals that we are allowed to take. There's a reason why we saved these until we were close to our integrals. This tells us that when we want to take the integral of something that looks like 1 over the square root of 1 minus x squared dx, we're going to get an arc sine out of that. When we want to take the integral of something that looks like 1 over 1 plus x squared, our answer will be in terms of the inverse tangent. And when we want to take the integral of something that looks like 1 over x times the square root of x squared minus 1, our answer will look like an inverse secant. And so the reason we've saved these until after we did the integrals was it just gave us some more ideas of some more functions that we can handle algebraically. We can take the integral of algebraically. And then of course we'd make Mr. Hendricks wear the wig if I forget to put the plus c, because you know I refuse to wear it. But all of these are indefinite the way I wrote them, so we should have the plus c. Your U form will come from these. So give me just a second to rearrange here. See, it looks like I don't have them on me. But your U form will come from each of these. If you have some constant here, you're going to get out this 1 over a times the arc sine of x over a, or u over a as the case may be, plus c. And the reason for it comes from the fact that we want to make this look as much like that as possible. We know how to handle it when there's a 1 here. We don't necessarily know how to handle it when there's an a here. The first thing that I think of in rearranging this would be to divide each term here by 1 over a squared. And then of course when you take the square root, the squareds won't matter so much, but we'll talk about that in a minute. I'm going to derive this algebraically. where this one comes from and focus on this rule that I have up here. So right now I have this idea of 1 over the square root of a squared minus x squared. I really want this first term to be 1, exactly 1. And so what I'm going to do is I'm going to multiply everything by a special form of the number 1. And the form I'm going to choose is the square root of 1 over a squared. Because when I distribute this in here, those will cancel and I'll get 1. And whatever I do downstairs, I've got to do upstairs as well. So up here, this will be the same thing as 1 times 1 over just an a, because we're taking the square root of 1 and the square root of a. Those will cancel. On the bottom, because they are both inside the square root, we are allowed to distribute the 1 over a squared in, and a squared times 1 over a squared is 1. And then here, x squared times 1 over a squared is x squared over a squared. And we get out that this is 1 over a times 1 over the square root of 1 minus x squared over a. And I'm going to choose to put parentheses around it this way. So this tells me that if I want to take the integral of this form, a squared minus x squared dx, it would be the same thing as taking the integral of 1 over a times the integral of 1 over the square root of 1 minus x over a squared dx. You would need to use u substitution here right now, and I would choose to make u equal to x over a. So my du is going to be equal to 1 over a dx. I've got that here. So when I write this in terms of u's, I've got 1 over the square root of 1 minus u squared du. This looks like my original form. Remember, the whole point of u substitution is to get it to look like this most basic form with the x's. And so now I'll get out the arc sine of u plus c which is equal to the arc sine of x over a plus c. Alright, and I had to pause the video for a second because I saw that this was different than this, but rest assured this one I was going off of memory for, and for many of the terms they include this 1 over a term in front. In this case it did not. So that's the proof of how we go from this form to this form and where this x over a comes from. Now when you do the integral of some of these other forms, like the arc tangent and such, you will still get that 1 over a term left outside, but go through this process and you'll see why. So good luck with these problems. I recommend watching these videos a couple times if you need to. Go through and do the derivation with me, and they'll help you as you go through and memorize these rules. I guarantee these are going to be ones that are going to come back again. So if you have any questions, just let me know.